Unit 10A is our introduction to oscillations. Oscillations, or oscillatory motion, refers to the repetitive back and forth motion between 2 points. Some objects that behave as oscillators would be like a guitar string, which vibrates back and forth, a buoy, which rises and falls with the waves of the ocean, or somebody on a swing, going back and forth between 2 points. The simplest kind of oscillator system is a spring mass oscillator, which has a spring attached to some massive object that moves back and forth. It's important to remember our spring equations. So we have an equation for the spring force, which obeys Hooke's law, as you see here, where delta S is the stretch distance from the equilibrium position for that spring. Additionally, we have a spring energy, which says that the energy is 1/2 the spring constant times the stretch distance squared. These equations will come back up in this unit. So you can think of the example of this ruler, or maybe like a door stop that you flick one way and it vibrates back and forth with its equilibrium position in the center. This would be an example of an oscillation where first the elastic object is pulled to the left and it feels a spring force to the right then to restore it back to its equilibrium position, and it gains speed as that force acts until the object passes its equilibrium point, and then the restoring force will act in the opposite direction to cause it to accelerate to the left this time, and this motion continues back and forth for a spring mass oscillator. So here is an example of a spring mass oscillator. You can see that we have our mass attached to a spring, and it's moving back and forth, left to right. As the spring stretches out, the restoring force gets larger, and as the spring compresses, the restoring force also gets larger in the opposite direction. This is an example of a spring mass oscillator, and more precisely, we call it simple harmonic motion because it is an idealized oscillator that does not have any damping. It will never stop oscillating or slow down. It will just continue like this permanently, and we can use math equations to model simple harmonic motion. The amount of time required to complete one cycle around that equilibrium position is called a period, and the period is measured in seconds. The amount of cycles passing in a given second is called the frequency, and the frequency is measured in hertz. And the frequency can be solved for by taking the inverse of the period. This means that hertz is actually units that are 1/seconds. That's what it would match up with. For a spring mass oscillator, the period of that system is determined only by the mass of the object on the spring and the spring constant. Remember that spring constant tells you how tight or rigid a spring is versus being loose and stretchy. The period for a spring mass oscillator is this equation, 2π times the square root of m/k. So this means that as our mass becomes greater for that object, the period will get longer. It'll slow down the oscillations. And as our spring gets tighter, as the spring constant goes up, the period will go down. It will oscillate at a faster speed. And the size of our oscillations is called the amplitude. This specifically is the maximum distance from the equilibrium point. So if we set equilibrium to be right in the middle at this equilibrium position, we can see that the amplitude is the maximum displacement that we get from this point. So we would take that point and think about how far it goes over here, and that is your amplitude. If we were to look at this on a graph, we would see that we have displacement on the vertical axis, time on the horizontal axis, and so this maximum distance that we get away from the equilibrium point would equal our amplitude. It's not the distance, it's not the size from one end to the other end, it is the size of the displacement from the peak to the midpoint. And if you wanted to calculate what the displacement was of a spring mass oscillator at any time, you would take that amplitude, here it's capital X instead of A because we have motion in the x direction, you would take that amplitude and multiply it by the cosine of 2π over the period times whatever time we are at. So we're going to gain some more experience with this equation that allows you to figure out where a spring mass will be at any time based on its period. And it's important to note that this oscillation could have started anywhere along this curve. So realistically, if we just shifted this graph to the left a little bit, it would actually look more like a cosine graph. But if we shifted it a little more to the right, as you see shown here, it looks more like a sine graph. It doesn't matter if you use sine or cosine, that'll just determine if you're starting at a peak or if you're starting at the midpoint. And we're going to gain practice drawing these oscillation graphs which track the displacement of an oscillator versus time. We call these history graphs. And you can extract out the amplitude and the period from these graphs. So that'll cover everything for Unit 10A. I'll see you in the next one.